All right, everybody. This is the start of this chapter 6 notes on discrete random variables. Then we're going to talk about continuous random variables. And I'm going to look at some examples. And this kind of ties in with the project that you guys did for chapter 5 over the break. So you kind of see how everything connects here in a little bit. So we're going to look at some bunch of different distributions. And yeah, we'll go from there. So what is a random variable? A random variable is just the outcome of some chance process. So it could be anything really. So a random variable takes numerical values that describe the outcome of some chance process. Okay, and so basic examples are going to be like flipping a coin. So basic, you have, like this, the sum like number of heads and 10 coin flips, right? That's a chance process. You could think like sum of 2 dice when rolled, 6 times, right? You can also get a little more what's the word? Maybe like abstract in the sense that you could think of like the heights of males and females, right? That is also a random outcome, right? You don't know what the height of a male or a female is going to be. So that's also another form of a random variable. Okay. Now, next thing, what is a probability distribution? It gives the possible outcomes and probabilities of a random variable. And so you have a couple of little properties that we need to know. So first of all probabilities need to be between 0 and 1. Kind of makes sense, right? We're not going to have negative probabilities. We're not going to have something that's more than 1. And the sum of all outcomes must equal 1, which is known as a CDF, cumulative distribution function. Okay, when it's cumulative, right, it adds everything up. So it's kind of the idea there. And so now that gets us to the actual, what is a discrete random sample? When you think of discrete random variable or discrete variables, it's just something that can only take on countable outcomes. So when the results of a random variable are countable, i.e. the number of heads, the sum of dice, right? These can only take on certain values, right? On the contrary, right, when we look at continuous variables, stuff like height, right, time, those are all going to be continuous random variables because they can take on any sort of value. So those are kind of some basic definitions. And now if we look at this, now we have like this problem here, and we're looking at imagine selecting a U.S. high school student at random, and then looking at the number of languages spoken. So one language, the likelihood is 0.63, 2 languages, 0.295. Okay. So first of all, show that the probability distribution of X is legitimate. All you have to do is add up these numbers, all these probabilities, and show that it adds to 1. Okay. And it does. Okay. You can make a little histogram for this. Okay. So when you make your histogram, you're just going to have your probability. Ooh, that's bad. You're going to have your probabilities on your y-axis, and then the number of languages on your x-axis. And then you can just draw those in, right? And then you should have, so this is number of languages. This is probability, okay? And so then when I draw these in, we're going 1 to 5, so 1, 2, 3, 4, 5. Try to make this as evenly spaced out as possible. Okay. And so now when you do this, only little thing that AP wants you to do is you're going to go above and below by a half, because these are discrete values. Like, you're not going to have 1.5. So what we're going to do is we're going to go from 0.05 to 1.5. It's going to be our first little bin. And this is going to be a height of point, if we go 0.1, 2, 3. Right, so 0.63 is going to be somewhere in here. So this is your first. When we look at histograms, we got to connect all these boxes. So that's why we do it this way. And so for the next one goes from 1.5 to 2.5. That's 0.295. So you have something like this. Okay, and then you can kind of keep going down. 0.65. I guess these get smaller and smaller. And then you get a cumulative distribution like that. Now, if you want to find the probability that a person speaks more than 3 languages, okay, this is just where you got to be careful. Or sorry, let me go. Oh, I missed a question. What's the probability they speak at least 3 languages? Okay, that means it's got to be more than 3. All right, and so if you speak more than 3, then you're looking at just 4 and 5. Okay, or I've read that back. I'm sorry. For part D, you're looking at just more than 3 languages, so you're looking at just 4 and 5. At least 3 languages, looking at 3, 4, and 5. Okay, so it's kind of just the difference between those. So make sure you're reading the question carefully. Okay, and then here we're tying it back into what we did last unit. Given the student speaks more than 1 language, what is the probability the student speaks 3 languages? So here on part E, you're just looking at the probability of, I'm going to call X be my number of languages spoken. So X equals 3, given that X is greater than 1. Okay, and if you remember a conditional probability formula, this is the same thing as the probability that X equals 3 intersection X equals 1. Divided by the probability that X is greater than or equal to 2. And here on the bottom of the denominator, because X has to be greater than 1, meaning that we got to start at 2 and go bigger. That's why they got this X is greater than or equal to 2. Okay. And so on this numerator, you should have 0.008. And then on the denominator, you can just kind of add these up and then make a little division, and then you'll get an answer. And so this is really tying in what you guys did over the break. You guys didn't know how to do these yet. I just wanted to see what you come up with. So here we're looking at a game called Corner Bet, and you want to find the average value. Okay, and so all you have to do is you're going to be multiplying these numbers together. So you're multiplying this by this plus the 8 times 4 over 38. That would be your expected value of this probability distribution. Okay. And so the way this works out is if I write this out here, and so let's read this problem real quick. So if one of these, to make this bet, a player places chips on the intersection of 4 number squares in the roulette table. If one of these numbers comes up on the wheel and the player bet 1, the player gets back his 1, gets his $1 back plus 8 more. Otherwise, the casino keeps the $1 bet. If X is the net average gained in the corner bet, the possible outcomes of this are here in the probability distribution. Okay, so the likelihood that you lose $1 is 34 out of 38. Right, that's where the casino keeps the money. The likelihood that you win $8, okay, is 4 out of 38. That's only four scores that this could happen. Right, and so if you keep doing these trials over and over again, let's keep making these bets. Okay, so we're going to just go, we're going to do -1 times 34 over 38, right? That's the likelihood that you 38. That's the likelihood that the casino takes your money plus 8 times 4 over 38, right? That's the likelihood that you win $8, right? So this is what's going to happen each time. Now you do this a bunch of times, right? You end up getting your expected value, okay? And so when we look at this expected value, what we can write, if we kind of expanded all that out, you get 34 times -1 plus 4 times 8 all over 38, just a common denominator there. And if you simplify this down, you get negative 0.05. So if after each bet, you're expected to lose 5 cents. Right. And again, the best way to think about that is each time I'm making these bets, these are my likelihoods, right? So the first bet, there's a 34 out of 38 chance that I lose the money. And then whatever this multiplication is, that that 32 out of 38 that I win. If you keep adding that over and over again, right, divided by a total number of times, divided by the total number of outcomes, you end up with this number right here. And so then that kind of leads into our equation for the expected value of a discrete random variable. And here we write E of x, which is E stands for expected value. And so that's why you see E of some random variable x, which we don't know. That's the same thing as writing the mean. So that's the same thing as mu of x. And that is equal to the first random variable times its probability plus the second random variable times its probability, its associated probability. So you're going to see I'm going to label all these with with 2s and 1s. And then you're going to keep doing this all the way until you get to x I times pi. So you're just going to do this for each individual, where the I stands for individual. I stands for individual. So if you had 10 different expected outcome or outcomes to this random variable, you would do this multiplication 10 times. So how do you interpret this? It is in a series of long trials or repetitions. This goes back to the whole law of large numbers thing. The expected value of blank is, whatever you get. And then you'll fill in the blanks with whatever that you're studying. And so if we're going back to the example on the first page, with the languages, the expected value is going to equal 1. So one language, okay, times its probability. So then I'm going to call it, this is x, where x is the number of languages, and then you have your p, so 0.63 plus 2 times 0.295 plus 3 times the third probability, which was 0.065, right? Go all the way to the end, right? Dot, 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 and you get to the end, and you end up with 1.457. Okay, and so the average number, or the expected value, so this is your expected value, E of x is equal to 1.457. And so what we can say is that the expected value for the number of languages spoken by high school students is going to be 1.45, 1.46 languages. Okay, and while it may not make sense to talk about 1.5 languages, we don't really care, right? This is just what we expect to see. Okay, so that kind of leads into the next point: is do the expected values of a random variable have to equal one of the possible values of the random variable? And no, you don't have to round it. It can be anything. Okay, so big thing here is do not round. So the expected value can take on any value, whether it's discrete or continuous, doesn't matter. That's just what we're expecting to see. And so we can kind of continue with this with some variance. I'll give you the variance is a little bit more complicated of a formula. So to calculate the variance, which we denote sigma x squared, is equal to x1 minus e of x squared plus, or sorry, I forgot the times the probability of 1. Okay, now plus x2 minus e of x squared times p2, and you're going to keep doing this, plus dot dot dot. Okay, and this basically can get rewritten as the sum, right? So I'm going to write this sigma here means sum, so we're just going to add all these things up of all the individual x's, so xi, minus the expected value of x, that quantity squared, times their individual probabilities. So this is quite a tedious calculation. It's really annoying to do. But what you're going to do is that for each one of your individual variables, so in the language problem, you're going to do this 5 times. So I'm going to take the first one, subtract away the mean that we just calculated, the 1.457, square that number, and then multiply by the probability. And I'll do that for 2 languages. So then I'll go 2 minus 1.457 squared times the probability, and 3 minus 1.457 squared times the probability. And then you're going to add all those up, and that's going to give you your variance. And so then we know already that standard deviation is just the square root of this. So then if I want to find just, it's just a different color. I don't rewrite the whole thing. Sigma x is just going to equal the square root of this guy. And so what does standard deviation measure? It's just a typical distance away from the mean. So how do you interpret this value? Standard deviation is a measure of how much the values of the variable typically vary from the mean. And so I'm going to start the calculation off on the language problem, but I'm not going to finish it. You guys can kind of finish it on your own. But I'll start it off. So what you're going to do is define the variance. And again, you're going to see how annoying this gets in a second. I'm going to take my individual x's. So I'm going to take my first x, which is 1, minus the mean, which we just calculated, 1.457. Square that times the individual probabilities. The probability of speaking one language was 0.630. Now I'm going to keep going. I'm going to just do one more, and then you guys can kind of fill out the rest. So 2 minus 1.457. You kind of see the pattern here. Squared times the probability of speaking 2 languages, which was 0.295. Okay, you can keep going. Plus, and then you dot dot dot, keep going until you get an answer of 0.450. And then define the standard deviation to square root this. And that equals 0.671. Okay, so we would expect the number of languages to vary from the expected value 1.45 languages by 0.67 languages. Okay. Now, on the calculators, what you're going to do is type data into lists. Okay, so list 1 will be your x values, wherever x can take on. List 2 will be your probabilities. And then what you're going to do is you go to one variable stats. Your x will equal list one. And then what you're going to do is you're going to change, there's a thing called frequency on your calculator. So you're going to change that to your probability list. Okay, and then you can use this to create histograms as well. So on your calculator, you can kind of type all these in. We'll kind of run through that in class. And the only thing that you got to be careful of is on the AP exam, if you just do this, they're not going to give you credit. So you have to do what I did earlier, which, where I started it off, and then you can go to your calculator. So here you need to show the first few terms of equations, then go to calculator. So you need to show some work. Okay. So while those equations that I said earlier, they're on your formula sheet. Okay, you still need to go through like what I did, and I started with the first two, or and then just write ... and then you can go to your calculator and then give a final answer. All right, what's a continuous random variable? Pretty similar to discrete, just another form of a random variable, except the only thing that changes is now the outcomes are no longer countable. Okay, so you have when the outcomes of some chance process are not countable. Right, as in they can take on any value. So some examples: height, weight, time, distance, right? All those are kind of random variables that can take on any value, right? Let's say you're looking at the distance that you run in, 2 hours. Okay, that's going to be a random. That's a chance process, right? It's going to change every time, and so that is some random outcome. Okay, so next question: is it possible to have a shoe size of 8? Is it possible to have a foot length of 8 inches? Yes, that is true, right? But now when you get to the next question, how many possible foot lengths are there? Right, there's an unlimited number of foot lengths here, right? But there isn't an unlimited number of shoe sizes, right? Shoe sizes only go by halves, right? The foot length, you could have 8.1 inches, 8.2, et cetera, et cetera, et cetera, right? So instead of doing histograms, right, what we're going to do is do density curves. And so how do we graph these things? We look at density curves. And the most common density curve that you guys have all seen before is the bell curve, right? That is a form of a density curve, right? And what I mean by density curve is it tells you like the probability of a certain outcome happening, okay? And so that's kind of the idea behind this, is so how do we graph these things? We look at distributions. And there are many types of distributions, right? You have skewed distributions, there's like gamma distributions. There's a whole bunch of different distributions, but in this class, we kind of focus on the normal because it's the one that's most commonly used. And so now, how do you find probabilities of continuous random variables? Well, if we have a normal distribution, we can use z-scores, right? And that's kind of the idea behind this, is that we have to check some conditions. But once we know our data is approximately normal, which is going back to the whole graphing thing at the beginning, okay? Once we know this exists, we can then use z-scores, right? But if we know our distribution looks something like this, okay, then we can't use z-scores, and then we're gonna have to use some other sort of techniques that we kind of talk about at the end of the year a little bit. Okay. And now, for continuous random variable, how is the probability of x equaling a related to the probability that x is less than or equal to a? So unlike discrete cases where you have these jumps, right? And if you think about, we talk about CDFs a little bit, but if you think about flipping a coin, for example, if you assign, let's say 0 is heads, so x is 0 is a head, and then tail is 1 is a tail. Okay. Right. And so basically what you have is you kind of have these probabilities that make these jumps as you go along. This is probably a bad example. Let me give a different example. So let's say you're looking at Yeah, we can look at the language example. Okay, so going back to the language example, right? The likelihood you speak one language is 0.63. So that's like, so you go up until 1, right? This is 0.63. And then you make a jump between 1 and 2, and then you speak, a little bit more. And it looks like, and then you have like this little stepwise function, right? And so it's kind of the same idea, except here, right now, that because we have continuous data, we're not going to have these jumps anymore, right? And the thing is that once you start looking at all these, and so if I draw a little continuous distribution, so I'm drawing a bell curve. Okay. Now what happens is, you keep getting smaller and smaller. So if I take, if I'm looking at this line here, okay, and as it approaches another line, right, this area is going to get really, really small. If I look at just area under this curve, right, if I try to calculate the area of this thing, okay, well, as I move this line at the beginning, and I get closer and closer to this area is going to get basically 0, right? And so what we're saying with the continuous data is that this probability that x is less than a and the probability that x is less than or equal to a are going to be the exact same thing, right? Because this area is going to get so small where it's going to be 0, right? But that doesn't happen in the discrete case because you do have those jumps. That's kind of the idea behind this. Okay, so since the probability that x equals a is 0, right? Because you have continuous data, there's no way of having like a specific line on this graph. And so the probability that x is less than a is equal to the probability that x is less than or equal to a. Okay. This right here is really good z-score practice. Try these on your own, right? This is kind of like a recap, a little refresher. We can kind of go through these together in class if we have to. But that's really good z-score practice. This last one here, this is working backwards. So I'm giving you the probability. So then you got to go to the z-score, find it, or go to the chart, find the corresponding z-score, work yourself backwards to get an x. Okay. This is really good practice. Try that on your own. But that's all of 6.1 video, guys. If you have any questions, please let me know and have a great rest.